Okay, so first we'll discuss the problem 2, that is from the calculus and recurrence relation mixed. So the problem says let a not equal to 1 by 2 and a n be defined inductively by this function. So inductive definition means that there is a relation between an and an minus 1. Show that for n equal to 0, 1 by 2, 0, 1, 2 and so on, an is equal to cos theta n for some 0 less than theta n less than pi by 2 and determine theta n. Okay. Using a or otherwise, calculate limit n tending to infinity 4 to the power n into 1 minus an. Let's discuss this problem. So we begin with taking the equation that an equal to under root 1 plus a n minus 1 by 2. Now we will take square on both the sides. So we get 2 times a n square equal to 1 plus a n minus 1. So I have 2 a n square minus 1 is equal to a n minus 1. Now we put in place of n minus 1. So we will get 2 times a n minus 1 square minus 1 equal to a n minus 2. And now in place of a n minus 1, we will put 2 a n square minus 1. So we get a n minus 2 equal to 4 a n square minus 3. Now in this equation, we again put n as n minus 1. In place of n, we put n minus 1 and we will get 4 times, by same logic, we will get here 2 times a n square minus 1 minus 1 equal to a n minus 2. So here we will get 8 a n square minus 5 is equal to a n minus 3. Here it will become 3. Sorry. We have substituted n as n minus 1 again. So this becomes a of n minus 3. Now we can keep putting this and we would observe a pattern that a n minus k is of the form 2 to the power n minus k, sorry, 2 to the power of k, 2 to the power of k a n square minus 2k minus 1. And now we will put in place of k, we will put n. So I will get a naught is equal to 2 to the power n a n square minus 2n minus 1. And we are given that a naught is equal to half. So since a naught is equal to half, we have 1 by 2 is equal to 2 to the power n a n square minus 2n plus 1. So on rearranging this, we will get an is equal to square root of square root of 4n minus 1 upon 2 to the power of n plus 1. So this is what we get an in terms of n. Now we can see that for all n greater than or equal to 1, 2 to the power of n plus 1 is greater than 4n minus 1. So our an is always going to be in between 0 and 1. Our an is always going to be in between 0 and 1. So this implies for all n belonging to natural, we have for all n belonging to natural, there exists theta n such that there exists there exists theta n such that cross of theta n is equal to an. Okay, since our and theta n will belong to 0 say pi by 2. Theta n belongs to 0 say pi by 2. So an is positive, an is less than 1. So there will always exist a theta such that cos theta is an, and theta n belongs to 0 comma pi by 2. So we can say hence proof. So this is how we done the first part, and therefore we can say that theta n is given by cross inverse an, which is equal to cross inverse of square root of 4n minus 1 divided by 2 to the power n plus 1. So this completes the A part of the second question. I hope the solution is clear. If you have any doubts, ask in the comments. I would like to explain it once again in brief. We were given the equation an equal to square root of 1 plus an minus 1 by 2. We square on both the sides and rearrange, and we get 2 times an square minus 1 equal to a of n minus 1. Then I substitute n with n minus 1, and I get 2 times an minus 1 square minus 1 equal to an minus 2. Then substituting an minus 1 from the first equation, I get the equation an minus 2 equal to 4an square minus 3. Then again substituting n with n minus 1. In a similar fashion, I get an minus 3 equal to 8an square minus 5. We can continue in the same fashion, or we can start observing the pattern that an minus k will be equal to 2 to the power k an square minus 2k minus 1. Now observing this pattern is easy because you see that every time we put an square, there will be 2 times an square here and minus 1 multiplied with an even number, right? And then minus 5 added, minus 7 added likewise. So observing this pattern is easy. So with that we get an minus k is equal to 2 to the power k an square minus 2k minus 1. Finally I put k is equal to n. So I get a naught equal to 2 to the power n an square minus 2n minus 1. I put a naught as 1 by 2, and finally I get this relation in an and n. So I have the value of an in terms of n, and this relation is true for all n greater than or equal to 1, not for n equal to 0. He has explicitly defined n equal to 0, the value of a naught. So for all n greater than equal to 1, we have 2 to the power n plus 1 is greater than or is greater than 4n minus 1. So I have 0 is less than an less than 1. So now I can say that for all n belonging to natural, there exists theta n such that cos theta n is equal to an, and theta n belongs to 0 say pi by 2. This is pretty obvious statement because your an is in 0 say 1, and if you see the cos theta n for theta n belonging to 0 say pi by 2, there will always exist a theta n such that cos of it is equal to an. So we prove the statement, hence proved, and our theta n is cos inverse an, which is equal to cos inverse of under root 4n minus 1 upon 2 to the power n plus 1. And this concludes the part A of the second question.